Let's take a closer look at polyethylene. You know, polyethylene is found in many packaging materials. It includes things such as plastic milk jugs, detergent containers, plastic baggies, and yet we have seen from the previous section, all polyethylene is made from the same monomer called ethylene. So how can this polyethylene have so many different properties? Our polyethylene is built from a monomer that had all hydrogens. And we saw through its addition propagation, we saw, just reminding, how the electrons in the double bond, we're understanding that through an initiation process, this radical, a radical is a species that has an unpaired electron, forces the unpairing of the electrons to just start create a linkage spot. So as this monomer begins to build into polymers, we see that the carbon-to-carbon double bond just simply becomes the linkage site as the structure begins to grow and grow. So polyethylene is made of the monomer ethylene, in which all of the substituents here are hydrogen. All throughout this monomer, we have hydrogen repeating over and over. So what makes something so stretchy as in saran wrap, or very rigid as in a milk crate? Those are all examples of polyethylene. We see that there is something known as low density polyethylene and something known as high density polyethylene. Each one of those is built of the same monomer called ethylene. So there must be a secret that lies in the structure in which these monomers are put together. And that structure has to do with the organization in which the monomers are layered upon each other. The different properties of polyethylene stem largely from the differences in the long molecular chains. These chains, remember, are millions and millions of molecules long. Imagine a polyethylene molecule to be as wide as a piece of spaghetti. And if this were the case, the molecule would be almost half a mile long. Can you imagine? So to this analogy, the polyethylene used to make plastic bags contains molecular chains arranged somewhat like cooked spaghetti on a plate, very disorganized. Can you envision this as cooked spaghetti on a plate? It lacks the organization of the molecules as they're lying around each other. So polyethylene that can be stretched is of low density. To be of high density, we start to see them arrange themselves in a different way. To be high density polyethylene, to create very rigid structures, these molecules start to simply lie on top of each other in a very organized fashion. The high density polyethylene is a very organized stack. The low density polyethylene is a very disorganized, as in a plate of cooked spaghetti. So what creates these disorganized or highly organized are the intermolecular attractions between the monomers as they start to build their polymer chains. I'm going to just remind us a little bit about a previous lesson on intermolecular attractions. Intermolecular attractions. Now, we talked a great deal about one in the water chapter. We called it a hydrogen bond. A hydrogen bond is a very unique intermolecular attraction in which we have an O bonded to an F, an O bonded to not an O. Please forgive me. I'm going to erase this. I just wrote water and got distracted. I need to make a correction. I apologize if you're erasing with me. H for a hydrogen bond is attached to an F, H attached to an O, or H attached to an N. A very specific criteria for molecules that have a strong attraction between, and remember how we drew these attractions, between molecules is known as an intermolecular attraction between the molecules. And that's what set up these qualities of water, such as high surface tension and a very high density and so forth. So a very, very strong intermolecular attraction. In addition to a hydrogen bond, we have what's called a dipole-dipole attraction, which we mentioned would occur between polar molecules. Just based on opposite charges, molecules that have polarity to them could also exhibit an attraction between molecules. And so if I just remember what polarity means, if I were to take a straight carbon chain, CHH, and all of a sudden put on a very electronegative element, such as chlorine or fluorine, we know that the electron density gets pulled towards the more electronegative element, and that would create this region that ends up to be slightly negative and the regions that end up to be slightly positive. This molecule is said to be polar because the electron distribution of this molecule is being pulled in this general direction, creating this negative region. Well, opposites attract, don't they? This molecule would be attracted to another molecule of its type based on the opposite charge. So if this region, as we stated, was slightly positive, you're going to see this intermolecular attraction between dipoles, between opposite charges of poled molecules. The strongest intermolecular attraction is known as a hydrogen bond. The next strongest is known as a dipole-dipole. And finally, we come across what this particular section is calling a dispersion force, the weakest of intermolecular attractions, and yet nonetheless it still exists. And I'm going to write intermolecular forces. How about that? Intermolecular forces, intermolecular attractions. Intermolecular forces are the attractions between molecules. Now, dispersion forces exist between non-polar molecule to another non-polar molecule. You can see why they would be a weak intermolecular attraction. So, what is a dipole-dipole? That happens to be between polar molecules. What is a hydrogen bond? Well, that happens to be a very strict criteria in which an H bonded to an F, O, or N sets up a very strong attraction, as we saw in the water molecules. Now, the weakest we said was dispersion force. And that's exactly what these long polymer chains have. Remember the molecule we just drew for polyethylene? It was just a straight chain of hydrocarbons. So this area, and again, these are all hydrogens up on these bonds here, but I'll just leave them off for time's sake. A straight carbon chain is a very non-polar molecule. There's exactly an even distribution between those particular hydrogens. The dispersion forces simply say when these molecules become near each other, they set up a temporary induction. So an intermolecular attraction called a dispersion force, the attractions between molecules that result from a distortion of the electron cloud that causes an uneven distribution of the negative charge. They become more and more significant the longer the chain becomes. Now let's repeat that. This molecule is nonpolar. It does not have any significant areas that are considered to be positive or negative, but more evenly distributed. Sometimes I talk and write, they don't come out just right, but they're evenly distributed throughout the molecule. When this molecule becomes in close enough contact to another molecule, they may speak to each other for a moment in time. So what we start to see is the hydrogens here, if they become close enough together, they're going to start interacting. And hydrogens, of course, would have similar charge. So you're going to start to see just a temporary induction of charge in which the electrons start moving away from each other. And the electrons, when they move away, are going to carry a negative charge this way and leave a slightly positive charge this way. And again, just that moment in time where two like molecules become near each other, they start to induce charges, and then that just repels them. So a very moment in time, very instantaneous, even, just a dipole that is induced and then is released. These dispersion factors are what we're going to consider when we think about ways that molecules can increase their dispersions, their intermolecular attractions. If I have a very long hydrocarbon chain, it has a very long surface area, it can interact with another long chain, and the longer the better when we're trying to create these dispersion forces. We want to give them plenty of room to interact. So longer chains have stronger intermolecular attractions. Longer chains have stronger dispersion forces. And again, that's because of surface area. The surface area, when they're large molecules, they have a wonderful opportunity at setting up these induction poles and create a dispersion force. Now, what about chains that are actually branched? What if I started to create carbon chains that had some branches to them? So again, we're looking at an opportunity. Think about monomers. This is a monomer. See, here is a monomer. Here is a monomer just attached up here. Here could be the other monomer. And see how I'm just grouping them. And what we're doing is just, instead of creating long straight chains, we're going to create branched chains. And this definitely affects the ability to set up an intermolecular attraction. The branched chains are like having little barbed wire on your fence. It's going to repel anything trying to get near it. So if I have this hydrocarbon chain that is branched and a hydrocarbon chain that is straight, there is less opportunity to set up an intermolecular attraction. These branched chains prevent the opportunity for a dispersion force, and therefore these are weaker intermolecular forces. So carrying that forward into our high-density polyethylene, we know that these properties give us a quite rigid and quite strong structure. Think of like a milk jug. Their monomers create very straight chains, and they stack well right on top of each other. When I have very straight chains stacking on top of each other, they have very strong intermolecular attractions or intermolecular forces. They have very strong dispersion forces because they're able to just stack and interact with each other. Those carbon chains can interact directly with the next straight chain, creating a very strong intermolecular field, holding the molecules quite rigid. Compare that to low-density polyethylene, which looked like that plate of spaghetti. And we start to see these branched chains. So maybe we start to see chains that have branches on them, and when I start to try to organize those particular straight chains, they're not doing it so well. They are disorganized because of those branches. They have a weak intermolecular force. They have weak dispersion forces because they have no opportunity to actually mix and mingle and get close to each other because these little barbs are hanging out, preventing that opportunity. High-density polyethylene has strong dispersion forces because of their straight chain. They have a great opportunity to interact between molecules, and therefore they have a very strong attraction to one another, very rigid structure. Because we have a weak dispersion force, less opportunity to interact, these low-density LPDE, low-density polyethylene, are very much weaker in attraction. They're the ones that are going to be stretchy, like a saran wrap, perhaps like a sandwich bag, and so forth. So even though they're built of the same type of monomer, again, the same monomer is C double bond C, and those constituents are all hydrogens. It's the way that they organize, either in a very straight line for high density, very strong intermolecular attractions known as dispersion forces, or in these branched type chains, creating this plate of spaghetti known as low density polyethylene, giving us characteristics or qualities that would be more like a saran wrap or a sandwich baggie and so forth, bubble wrap even, things like that. So plastic bags stretch until it necks and it might even tear. A representation of the necking at the molecular level is what that original slide showed as up here. So the stretching that occurs for low density, we see a highly disorganized plate of spaghetti. In high density polyethylene, we see a very organized plate. So what might this look like? Which of the following exhibit London dispersion forces? Think of this as the intermolecular attraction between non-polar molecules. I talked about dispersion forces being the weakest type of intermolecular attraction. I talked about something called dipole-dipole, which is a stronger attraction. They need to be polar molecules, and then the strongest of all is the hydrogen bond. So let's review just so we have it all in one spot. Dispersion between nonpolar to nonpolar, right? So we're looking for the intermolecular attraction from nonpolar to nonpolar. Dipole-dipole is that attraction between polar and polar molecules. And hydrogen bond exists between molecules, but a very specified type of polarity between HF, HO, or HN. We're being asked which one of these would have dispersion forces. So we're looking for non-polar. Alrighty. Helium is just a simple atom. It has an even distribution. Helium would have, remember what helium looks like. We have just 2 protons, 2 neutrons sitting in a nucleus, and outside we'd have 2 electrons moving around in the orbital, evenly distributed so that its electron cloud would be nonpolar. HCl, with its Lewis dot, clearly shows that this is a polar molecule with the uneven distribution of electron clouds over here, creating a positive sign here. We could see this is clearly a more electronegative element, pulling the electron distribution on the chlorine. So this is polar. This would actually have dipole-dipole interactions. Water, we know, in terms of its Lewis structure, has a very strong intermolecular attraction. It exhibits hydrogen bonding. And chlorine, well, diatomic chlorine, 2 chlorine atoms, single bond between them, has a complete uniformity in its electron distribution. It is also a nonpolar molecule. Dispersion forces exist between nonpolar to nonpolar. Rank the following of strength of our dispersion force interactions between molecules. Rank them from the weakest to the strongest. The 3 that were given happen to be halogens, and the halogens come from group 7A on our periodic table. So on your group 7A, do you see fluorine? Underneath that lives chlorine. Underneath that lives bromine. Underneath that lives iodine. So this is an important periodic trend. We know that fluorine, being in our first row here of group 7A, would have the least amount of energy levels as we're building the atom. And the iodine would have the most amount of energy levels as we're building our atoms. Atoms get bigger as you go down the column. And remember, dispersion forces increase with increasing surface area. So dispersion forces increase with increased surface area. Spelled that wrong. Alrighty. So which is the atom that's the biggest? If fluorine, then we have chlorine, then we have bromine, and we have iodine, which has the largest surface area. Of course, the largest atom, the heaviest atom, would have the greatest dispersion force. And again, I should draw these as diatomic molecules because that's what they're living here as. So the element here, F to F, chlorine to chlorine, bromine to bromine, iodine to iodine, are all single bonds. The greatest surface area, that of iodine. Then we would have in the middle bromine, and the weakest would come from the smallest diatomic molecule, chlorine. Dispersion forces increase the heavier, longer, or more surface area the molecule possesses. So the same idea, we're going to rank the dispersion forces between the molecules. We want the strongest. Remember, this has the most surface area, to the weakest, which would have the least surface area. Here we have our first example, carbon, carbon. Now I see some CH3s and then a CH3. I'm going to draw this for us, and I'm going to just kind of show where I'm drawing it over here. I have a CH3 that looks like this, attached to a carbon, CH3 attached to a carbon. Now attached to this carbon is two more carbons, so that's what it's showing us. Here's the CH3, here's the CH3. First carbon has 3 hydrogens on it. The next carbon has 2 CH3s attached to it. And then finally, the last carbon is CH3. Notice how this is a highly branched carbon. Alrighty, something to consider. Here we have a very straight chain. And how many carbons long is it? 1, 2, 3, 4, 5, 6, 7 carbons in a straight chain. This is also a straight chain because I don't see any parentheses or so forth like we did in that first column. We did 1, 2, 3, 4, 5 carbons in this straight chain. So of course we know the branches disrupt the opportunity to create an intermolecular attraction. So they disrupt the dispersion forces because those 2 carbon backbone chains here, the carbon chains can't get near each other. It's like having a little barb hanging out. So if this disrupts the opportunity to set up the dispersion force, it of course is going to form the weakest dispersion force. The longest carbon chain has the most surface area. It is going to have the strongest dispersion force, and therefore the one in the middle would be the 5 carbon straight chain. Dispersion forces are intermolecular attractions. When we create branches, just like in a low density polyethylene, those intermolecular attractions are disrupted, and we end up with some weaker attractions that create the opportunity for stretching and so forth. But the longer straight chains set up an opportunity for high density polyethylene because those molecules can just stack right on top of each other, creating a very strong chain. This would look like our plate of spaghetti, just very random organization, and high density are these long chains stacked right close to each other. So this branching alters the physical properties of our polyethylene. Our low-density polyethylene is highly branched. Our high-density polyethylene is a very straight chain with very strong intermolecular attractions known as dispersion forces. The longer, straighter chain, the higher the intermolecular attractions, the more rigid the molecule becomes. The more branched our polyethylene is, the less structured it is, and we start to see that it's able to be stretched and with a lower, less rigid structure. Which of the following contains factors that affect polymer properties? The chain length, intermolecular forces, and the molar mass of the monomers. Choice 2, chain length, carbon-hydrogen bond strength, and the extent of branching. Chain length, intermolecular forces, and the strength of CH bonds. Chain length, intermolecular forces, and the extent of branching. Molar mass of the monomers is identical. The molar mass of the monomer is always the same for both high density and low density, and since we have the same building block, they're identical. That lets me toss out the first choice. The strength of the carbon-hydrogen bond is exactly the same in either high density or low density polyethylene. That doesn't change. The strength of the bond is identical. What it has to do with how they're arranged, doesn't it? It has to do with the extent of the branching. More branching is low density. Low density is lots and lots of branching, preventing any type of structure, and high density is very straight chained. And so our chain length, the longer the chain, the more opportunity we have to set up greater attractions known as dispersions. Those dispersion forces are the intermolecular attractions, and I want to prevent branching if I want the structure to be very rigid and strong. When we consider that there are over 60,000 synthetic polymers today, most of them are built of what we collectively called the Big Six. Today, more than 60,000 synthetic polymers are known. Although polymers were developed for many specialized uses, 6 types account for roughly 75% of those used in both Europe and in the United States. We refer to these everyday polymers as the Big Six, and you can see them in the table in section 9.5 on page 381. We refer to these in table 9.1 as polyethylene, both in low and high density, polyethylene, both in low and high density. We see polyvinyl chloride, PVC, polyvinyl chloride. We see polystyrene, polypropylene, and polyethylene terephthalate. Polyethylene terephthalate. Notice this terephthalate, the pH is silent. Terephthalate. And we're going to talk more about that in a moment. We also see this table listing properties of all 6 polymers. All are solids that can be colored with pigments. All are insoluble in water, although some dissolve or soften in the presence of hydrocarbons, fats, and oils. All are what we refer to as thermoplastic polymers. Thermoplastic polymers. That means that with heat they can be melted and reshaped over and over again. However, they exhibit a range of melting points depending on the route in which they were manufactured. Of the Big Six, polyethylene has the lowest melting point, with LDPE and HDPE melting at about 120 to 130 Celsius degrees respectively. In contrast, polypropylene, PP, polypropylene, it has a melting point of 160 to 170, so it's much higher. And of course, depending on the arrangement of the molecules, the polymers have a varying degree of strength. So just as we talked about, the strength relies on the ability to form the intermolecular attractions called dispersion forces. Taking a closer look with me at this chart, notice we just spent time with the polyethylene, both in high density and in low density. The hydrogen here is in blue. If the hydrogen is substituted out with a chlorine, we go from the ethylene monomer to a vinyl chloride monomer, which when I create repeating patterns forms polyvinyl chloride. Vinyl chloride forms polyvinyl chloride. And you're going to find those in plumbing pipes, for instance. You commonly hear it called as PVC. If we substitute out, instead of the hydrogen position of ethylene or the chlorine position of vinyl chloride, and we put on a phenyl group. A phenyl group is a six-sided carbon ring in which you see alternating double and single bonds. I should have went straight up there. Let me correct that. That's better. Six-sided, and we have double, single, double, single, double, single, alternating double, single bonds. And at each carbon, we have a hydrogen, creating a very non-polar substituent group. Remember, this is the one that's attached to the monomer here. So this particular carbon is the site of attachment. This particular structure is called a phenyl group. It is the monomer built for polystyrene. Styrene is the name of the monomer. Polystyrene is the name of the polymer. You might know this as its industrial name as styrofoam. You'll see it making foam cups, any type of insulation, food packaging trays, egg cartons are all made of polystyrene, which is the chemical name for a styrofoam manufacturing name. If we take off the H, substitute it with Cl, take off the H, substitute it with a benzene, we're creating different monomers, this phenyl group here. And the last one here says we can substitute on the methyl group, CH3, and create polypropylene. The monomer is propylene. Repeating the pattern creates polypropylene, abbreviated PP. And these are things like bottle caps, yogurt containers, margarine containers, carpeting, and so forth. So you can kind of get an idea of this. Now, all of those monomers, up until this one here, were built by this process we called an addition polymerization. That's what we talked about in terms of unpartnering each electron and creating a radical, and the chain would propagate with like radicals. You know, one chain right after the X, monomers were exactly the same. Monomers are the same as they propagate to the polymers. Because now what we're going to introduce is something called a condensation reaction. And a condensation reaction, perhaps that word might lead you to think it's going to involve water. And we're going to take out a water to create a linkage spot between two different monomers. In the process of condensation, we add two different monomers by removing a water molecule to create the linkage site. And we're going to practice that in a lesson here on creating condensation polymerization. So the purpose of the big six was to remind us that there are three more polymers that make up the big six. We have styrene, polypropylene, ethylene glycol, and terephthalic acid. Those are the monomers that we're going to learn create polyethylene terephthalate. This is by that condensation reaction. Alrighty. So we'll talk about that chemistry. I also wanted to make mention of the way that we can arrange monomers can vary in terms of how they arrange themselves. So let's talk about that. Let's take a look at this particular structure. Has the chlorine position at carbon 2, hydrogen is at carbon 1. And notice that it's exactly the same as you repeat down the chain. Alternating carbon 1, carbon 2 is what we refer to as a head-to-head, a head-to-tail, or a tail. Oh my gosh, I'm getting distracted as I write and try to talk. My apologies. Please bear with me. A head-to-tail where carbon 1, carbon 2, carbon 1, carbon 2 simply repeat themselves. Head-to-tail. So what about here? All of a sudden now I have carbon 2, carbon 1, carbon 1, carbon 2, carbon 2, carbon 1, carbon 1, carbon 2. What pattern are we seeing? Well, if carbon 2 contains the chlorine, and I just clearly labeled as we went, we now see that they're hitting tail to tail. You could call it head to head as well, but tail to tail. So you repeat. Carbon 1 is attaching to carbon 1. It ends with 2, so it's going to attach to the one that it's like. So if this is the monomer where chlorine is at position 2, it is now going to attach to the same one that it's like, giving me carbon 2 at the linkage site. And if carbon 1 is now at the end, it is going to bond to the one that it's like, creating a head-to-head linkage. And the third way that they can organize themselves is just random. Here we have carbon 2 attached to 1. This would be the first monomer. 1 to 2. 1 to 2. 2 to 1. 2 to 1. A complete random order. The abbreviated structure for polyvinyl bromide with N repeating units is shown below. So here at our carbon 2 position, instead of chlorine for polyvinyl chloride, we substituted a bromine, and now we have polyvinyl bromide. Draw a molecule with 4 repeating units, connecting them head to tail. Head to tail is a predictable repeating pattern. So let's begin by drawing our first monomer, in which we would have 2 hydrogens on carbon number 1, and we'll have a bromine hydrogen at carbon number 2. So let's just kind of remind ourselves, we're calling the first carbon 1 and the second carbon 2. I have to draw in 4 repeating units, so I'm going to zip my backbone there. There's monomer 2, monomer 3, monomer 4. And in position that's head to tail, we're going to put in a very predictable pattern in which, now let me just number, carbon 2 attaches to 1, 2, carbon 2 attaches to 1, 2, 1, 2, and so forth. And now I just need to fill in. On carbon 1, we always have 2 hydrogens. And at carbon 2, we have a bromine and a hydrogen. And we see this predicted pattern of head to tail. So by the time we were drawing 4 monomers, we created a structure that was 8 carbons long. Carbon 1, 2 is our first monomer, carbon 1, 2 is the second, 1, 2 is the third monomer, and finally the fourth monomer. It's not as easy talking and writing at the same time. And notice that each and every time we place there the bromine at carbon 2. Now it looks like on sapling we should not have drawn in this extra linkage because it only asked for 4, so we're going to terminate the bonds there. We're doing so well. The polystyrene foam used in styrofoam cups is made by the same addition process. The only difference now is our grouping on our carbon 2. We've grouped it having a hydrogen for polyethylene, a chlorine for polyvinyl chloride, and it can be this phenyl group to create polystyrene. And again, notice we practice writing out, these are just really carbons in a 6-sided ring. Every corner here represents a carbon atom, and notice that we had an alternating double, single, double, single, double bond. What's not drawn in there, but we know they're there, are the hydrogens that complete the octet of those carbons. So in terms of its functional group in a molecular formula, you have C6H5. This missing hydrogen is the linkage up to the original monomer carbon up here. So these functional groups really do play a role in the type of chemistry we're seeing in terms of intermolecular attractions. Suppose what we have on our monomer, I mean, it can have a wide variety. At this position, we have an opportunity to create all kinds of different monomers to build polymers from. And the stronger the intermolecular attraction we have here, the stronger the polymer would become. So what are some other functional groups we can actually add to this position to create the monomer? One opportunity is called a hydroxyl group. A hydroxyl group is an OH functional group. Now in chemistry, organic chemistry specifically, we need to know that that functional group is called an alcohol. So if I were to place an OH in this position, I have created an alcohol functional group in organic chemistry. Of course, this is a very polar region to the molecule, so I would predict very strong intermolecular forces, and the polymer would have great strength. Another functional group we could add to the position to create a monomer is called a carboxylic acid. So in this functional group, I could have C double bond O, OH. C double bond O, OH. These are known as carboxylic acids. And I'm just filling in the dots so that they look like they have the 8 octet. Notice this acid, I always tell my organic students, COO. If you see COOH as a functional group, COO. A carboxylic acid is its name. Carboxylic acid is a functional group in which the carbon at position 1 is double bonded to an oxygen, single bonded to an O, and then H. C double bond O, OH, is a carboxylic acid. An ester. An ester is an organic functional group that contains a C double bond O, OC. So notice what's happened. Instead of an H at the end, we have another carbon group to create an ester. So this is not at the end of a chain, but in the middle. So again, let's stress, we have our monomer, and in this position, we could place a functional group called an ester. The ester would be attached by this carbon here, and I would see a double bond O, and then an O, and then another carbon, and it would probably terminate here with a CH3. It could be a longer chain, doesn't matter, but this would terminate the chain when I put the 3 hydrogens at the end. And again, notice this is also a very polar monomer. Because of these electrons on the oxygen, this would have the opportunity to set up dipole-dipole interactions, a very strong intermolecular attraction. We need to know that these are called esters. An amine is a functional group that contains a nitrogen attached to 2 hydrogens. An amine is an NH2 functional group. The monomer that would contain the amine would be at this position where nitrogen is attached to two other hydrogens, and it also has a lone pair completing its octet. This is also a very polar molecule, so very strong electromagnetic attractions or intermolecular forces, and we need to know that this is called an amine group. And the last we'll need to recognize is called the amide. An amide, when I put it into a monomer, has this position attached to a carbon, and that carbon now has a double bond O and now attached to an NH2. And again, the nitrogen has a lone pair to complete its octet. The oxygen has two lone pairs to complete its octet. This is called an amide. An amine directly attaches the carbon-nitrogen to the monomer. An amide, the nitrogen is attached to a C double bond O, which is attached to the carbon in the monomer. But all of these different functional groups are easily substituted out in this position to create different types of structures as we learn about monomers coming together to make polymers. So this is a practice on your sapling recognizing those organic functional groups. Which ones are the amides, it asks. Which ones are the amides? Well, I'm trying to get my screen to not. We see the carbon, 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 straight chain. I see no functional group on here at all. I see carbon CH3, nitrogen NH, CH2, CH3. You know, to look for an amide, what are we looking for in amides? And it might be handy to just pull that slide back up. An amide, we see, has a carbon double bond O, NH2. Carbon double bond O, NH2. So as we pull this up, do you see that structure anywhere? Carbon double bond O, NH2. I'm looking here, but I don't want you to be fooled. Carbon double bond O, NH2. They have to be next to each other, so this is not. Let's see, C triple bond N, nope, nope. Look down here, finally. I have a C double bond O directly next to the nitrogen in its functional group. This creates an amide. An amide we have to have in the same structure, C double bond O directly next to it, the NH group. It's not NH2 because there's just another carbon attached to it, but this is your amide. I'm not saying that they are in the same compound, but they have to be directly next to one another. And I think I hopped over a slide. I'm going to back up and look for the alcohol. Remember the functional group of the alcohol? It contained an OH. An alcohol looks like an OH. So when we look at this particular slide, do you see any alcohols? Look at here. Here's an alcohol. There's an OH group. This is an alcohol, has an OH group. Nope. Now remember, this has an OH, but it's attached to a C double bond O, so this is a carboxylic acid. So that's not an alcohol. So we're looking at OH in structure B, and we're looking at two alcohol groups in structure C. I don't even see F. Here it is. Oh, and this is water. Don't be fooled. This is OH in both directions, but HOH is not an alcohol, it's water. So we're not selecting that. So here we found two structures that were alcohols. We talked about our amides. What about the amines? Again, another practice with this chart where we talked about functional groups. Amines have nitrogen and a hydrogen attached to each other. So we're looking at just the nitrogen, not next to a C double bond O. So let's find the amines. something that contains an NH group. I find one here. No. No. That has no nitrogen. Here's one. That's a yes. And the last one is water. So here we found two examples where we've found our amine group. Are these pretty easy to spot? Carboxylic acids. Again from our chart, carboxylic acids with our COOH, C-O-O-H, COOH. With our carboxylic acids, we're looking for a C double bond O, OH, all next to each other. I can eliminate this choice. They have no C double bond O. I can eliminate this choice. There is no C double bond O. Here's a C double bond O, but not next to the OH. Does not meet the criteria. This has a C double bond O, but does not have an OH. And finally, here's one, COOH, C double bond O, directly next to the OH. That's a carboxylic acid. And this has none of the criteria. We'll keep practicing as you're getting better. Which ones are the esters? If you need a reference, go back and find your chart, esters. An ester has a C double bond O with an O right next door within the chain. C double bond O, C. I see nothing with double bonds. Look at here. C double bond O, O, C. There's our ester. Now look at here. C double bond O, not next to an O, so that does not meet the criteria. C double bond O, but no other oxygen, so that's a no. C double bond O, but the oxygen is not attached to another carbon, so this is what we called a carboxylic acid. That's not an ester. And letter F, COC, does not have a C double bond O, and therefore it does not meet the criteria. Here we're asked to practice labeling the functional groups. C double bond O, OH. C double bond O, OH. We wrote that as COOH. That's called our carboxylic acid. Look at here, it's at this end as well. Carboxylic acid, COOH, C-O-O-H. Here we have our NH2 group directly attached to a carbon. An amine group has an NH2, and again, those are exactly the same. These are the monomers used in building nylon. Nylon, of course, is a very strong polymer. We wear those on our legs to keep warm. COOH, carboxylic acids, and the amine is the NH2 group. We're going to pause our lesson here. It's been a long lesson, so we'll pick up with the next category of reaction called a condensation reaction. Remember, we did great work with our first category called addition reactions. Here we're going to talk about a second way that we can form polymers by condensing, which means to remove water. Great work, and I'll meet you back here when you're ready for your next lesson.